the beginning. Alkenes is a topic that we've been doing since the beginning of our organic chemistry journey, pretty much since Form 5, but we always keep on adding and adding and adding. Up till now, you're at the point where you are doing addition reactions that follow Markovnikovs Rule. Now, Markovnikovs Rule, as we've seen yesterday, is a product of different energy diagrams, okay? So that must still hold true. Energy thermodynamics is something that you cannot break. You can have a kinetic and a thermodynamic product, but you have to look at the energy diagram. You have to see what's really happening. You have, for example, yesterday, we've seen that the fluorination follows as a kinetic product, whereas bromination follows as a thermodynamic. The bigger the difference in the activation energy, the more that the thermodynamic product will be favored. Now, yesterday we were speaking about early transition step and late transition step, okay? This is how easy it is to achieve it. Normally, something that is early transition step means you need very little energy. Late transition step means you require quite a lot of energy and you have to heat. Now, for alkenes, we're normally used to having a double bond and you add two items, for example, HCl, Br2, H2O, and you get the addition over the double bond. Now, for this reaction, delta S would be negative. Delta S would be negative, which means that for these reactions to be possible, all these reactions must be exothermic. Any reaction here that is not exothermic would not be thermodynamically feasible. They would not be spontaneous. Why? Because you have 2 moles, normally 2 moles of gas, to give 1 mole. Okay? Now, you might find exceptions. If you go on the dark side of the internet, you might find some equations that might be endothermic. Okay? But normally, these reactions have negative entropy, and therefore, these reactions would thus also have or require an exothermic reaction. Okay? Remember, this equation will be your friend. So if entropy is negative, this term then becomes positive, and for delta G to be negative, delta H must be more negative than T delta S. And here, in fact, you have Fu delta I, delta G's, okay, or Fu delta, okay, and you can see that they have to be negative. Now, for the one where it's a problem, or there's a problem, it's for water. If you are trying to add water, in fact, we normally use a catalyst. The catalyst is H2SO4. Why? Because H2SO4 can easily add onto the double bond. By easily, you still require 140 degrees Celsius, but it's possible. And then removing the HSO4 minus as a leaving group and substituting by an OH minus, that would be very easy. So in fact, normally the alcohol is prepared first via an addition reaction, then via a substitution reaction, okay? The OH minus would then replace the HSO4 minus. We'll be speaking about those reactions later on. Now, very important, okay? Earlier on, in the previous slide, I didn't really discuss it. If you were to use the entropy change is gonna be approximately T delta S around 10 kilocalories per mole. Okay, now I don't normally love using kilocalories, but Volhard uses calories because it is an American book. Okay, and he's an American lecturer at the end of the day as well. So here we can see that For water, it is an exothermic reaction, but it's only -11. So at the end of the day, delta G will be approximately -1. Now, you might tell me, but delta G -1, isn't it negative? Yes, but delta G equals 0 would be a perfect equilibrium. Now, in reality, all the values, all the definitions, they are dependent on the concentration. So delta H and delta S, they will be dependent on the concentration of the reactants, which means that depending on where the reaction lies, you're gonna either have the alkene being formed or you're gonna have the alcohol being formed. And that's why you can have the reversible reaction and you can remove H2O to form the alkene. Because by increasing the temperature, you make T delta S bigger and you make the backward reaction favorable. So remember, 140 degrees Celsius to go from the alkene to alcohol. Okay, 180 degrees Celsius to go from the alcohol to the alkene. And that is because at that point, you make the delta S bigger than delta H, and therefore the reversible reaction would be the most favorable. So, we are also used to having hydrogenation. Now, hydrogenation does not really follow the electrophilic addition mechanism, as in, you don't really have the electrophile taking hydrogen, breaking the hydrogen bond, forming an H minus, like you would have in Br2. And that is something very important. Why? Because we need a catalyst. And this catalyst is normally either palladium and carbon, platinum dioxide, platinum. You can have nickel. There are a number of different catalysts. Palladium and carbon, it's very, very dangerous. Okay? For example, I used it once and I was using methanol. Palladium and carbon will ignite methanol if in contact with air and it will burn. Methanol has a very clear flame. So what happened? I was cleaning my glassware. Okay, the one step everyone told me, as long as you get to the cleaning stage, you're safe. And I was so happy that I managed to make it to the cleaning stage. And at one point, I see some small flame. Now, methanol burns really with a really clean blue flame, so you can't really see it. So the fact I could see the flame meant there was quite a big fire. And I was like, that's fine, I will let it burn off. But by mistake, when I was turning away, and I was a little bit in shock, I hit the conical flask, and the methanol went onto the bench. Again, that was fine. But because I'm a very bright person, I decided to try and switch off the flame. It was like, we are a small flame, what can happen? With my lab coat. And the lab coat caught on fire, meaning I caught on fire. And in fact, I burned part of my hand, part of my both hands, and one of my arms. And thankfully now it's fine. But it was a bit of a shock. So pay attention whenever you're using palladium carbon. If you're ever using it, pay attention. Make sure you have a very good nitrogen supply, because in contact with air, and it will burn. Now, these catalysts are heterogeneous. So we'll actually see how these will work. And heterogeneous catalysts normally interacts very differently. It doesn't use this variable oxidation state that you have done for something like iron between the iodide and I think it was S2O32 minus in your case. Okay, you do it very, very differently. Okay, so what happens? It lowers the activation energy. Okay, and it does that. Okay. It does that simply by, let's see if I can draw it somewhere. Okay, I'll draw it on the whiteboard. It does that simply by actually, so you'll have the nickel, okay, and you'll have the hydrogen, and you'll have your alkene. So there would be interactions between the double bond and the hydrogen. But these interactions would actually weaken both the C double bond C and H single bond H, meaning it would make it a lot easier for the reaction to take place. Okay, it would make it a lot easier for the reaction to take place. So again, do keep this in mind, because this mechanism is not a true electrophilic addition as you are accustomed to. Okay. Then, stereochemistry, because of what I just said, okay, this will be syn addition. Why? Because they're gonna be from the same side. The hydrogen and the double bond will be, the hydrogen will take the double bond from the same side. Both hydrogen will on the same side. So this is syn addition. Okay. Now, have you heard the term syn and anti at the moment? Syn meaning if you have a double bond, both are gonna attack from the same side. Anti would mean that you have both sides. So this would be anti. Okay, so this would be anti, okay, but here you have syn. And syn means they are both attacking from the same side. And here you need to ensure, that you realize that that means that whatever group is going to be present is going to be pushed downwards, okay, or upwards, doesn't really matter. They're going to be a racemic mixture. So even though here he gave you the SR, where the two alkyl groups are going to be pushed downwards, it's equally probable that you will have the pushing upwards perspective as well. Okay? It's probable that we're going to have the pushing upwards perspective as well. Now, the second reaction is something that I find truly fascinating. Because here you are adding deuterium, and deuterium will actually create a new chiral center, because deuterium and hydrogen, whilst chemically they are the same, you can actually see that they're gonna be different structures, okay? Especially deuterium and hydrogen, where you have doubling the mass. So even physical properties, there would have some slight different properties. Okay, and here you have so Horus conformation. Okay, so you change it and you're gonna see through the double bond, through the single bond created. Okay, here you are seeing through the single bond created. Okay, so you have electrophilic addition. Okay, now electrophilic addition, you can't control whether it's going to be anti or syn. Why? Because your intermediate is going to be planar. So your intermediate has a similar chance of being attacked from the top as it is of being attacked from the bottom. Okay? Which means that you'll get, again, a racemic mixture, but this time they're gonna be either on the same side or on different sides. So you're gonna get, if you have a chiral compound, you will get 4 different structures. Okay? Depending on how many chiral centers you create, but a maximum of 4. And it's something that you need to pay attention for. Apart from this, always pay attention. We're going to be speaking about this later on. Whenever you create a carbocation, you can have rearrangements. Okay, so we'll be speaking about rearrangements later on in this course. Rearrangements are a headache. Okay, rearrangements are a headache. Tertiary carbocations are the most stable. Therefore, the structure would try to create a tertiary carbocation. And here you will have something of what you've been doing up till now. You have addition of HI. We normally don't draw stereochemistry, we just add the HI and we try to see what happens. Okay, and at this point, you have to try and follow Markovnikov's rule. Proton adds to the last substituted carbon. Or, as you might know it, the proton will add to the carbon that has most hydrogens. Now, I don't really like the definition as the proton. That should be electrophile. Now, Markovnikov's rule does state the proton, but what happens if you are adding something like BrCl? Okay, this would be delta plus on the bromine and delta minus on the chlorine. And at that point, you would have to note that the bromine will be your electrophile. The bromine will take the place of H plus. Okay, so that would be something that you would need to be utterly careful and utterly confident about. And this is the origin of Markovnikov's rule. Okay, as we've done yesterday, or as you saw yesterday, this is going to be a situation where you are going to actually be able to add a proton onto the double bond. Okay, but that means we're going to have a carbocation. Now, carbocations, because of hyperconjugation. Now, if anyone of you is still unsure about hyperconjugation, I uploaded a video yesterday. If after that video you still don't understand hyperconjugation, send me an email. Okay? Then you will have either a primary or a secondary carbocation. The secondary carbocation is favored because this is much lower energy step when compared to the primary carbocation. Therefore, this will give you the thermodynamic product. Okay? And here you can see. Now, in reality, it's not completely not observed. It depends on the difference between those two steps. Okay? It completely depends on the difference between those two steps. Okay? The bigger the difference, the more the thermodynamic product will be favored. Okay? Therefore, that would be the one that you will produce as a compound. Please note, important to note, the two products, they are not identical. They do not have the same energy structure. So you might end up in a situation where the most stable product, okay, the one that has the lowest energy might not be the thermodynamic product. Okay? Sorry, might not be the kinetic product. But kinetic would be the one that is created faster. Okay? But here you can see, in this position, in this situation, you are going to end up with the secondary carbocation being produced. Okay? With the secondary carbocation being produced. So here it is both the kinetic and the thermodynamic product. Okay? So if anyone is confused, got confused because of that, this is both the kinetic and thermodynamic product. So what happens? Then you can start doing some reactions. Okay? So the Markovnikov hydration. So this is what you've been doing up to now. You add the H plus. Okay? Once you add the H plus, when you protonate, you can either have the H2SO4 attacking or HSO4 minus at that point, or you can have water. If your solvent is water, this reaction can happen with catalytic amounts of H2SO4. Okay? If you don't want to use your solvent to be water, because sometimes that's not going to be the ideal solvent, then you can use H2SO4, which will add onto the alkene itself. Okay? Which is probably what you have done also at A11. Now, it's an equilibrium. Because it's an equilibrium, adding H2O will shift it to the right and will shift it to your product. But this reaction obeys Markovnikov's hydration. So what happens if you do not want to obey Markovnikov's rule? What happens if you want to get the anti-Markovnikov product? Okay, and there is also a reaction that will cater for that. So that is something that we will be able to then discuss later on. Okay, so you must also pay attention. If you have something like alkene, such as butene or but1ene, rest assured that but1ene is not going to exist in solution for long. Okay? Because it will easily end up giving a situation where it will become but2ene. And okay, we have the mechanism afterwards because I was gonna draw it. And this is something that is very important to know. Okay? Because when you produce an alkene, make sure that your alkene is produced in a neutral solution. Because alkenes, unless it's the most stable alkene, it will rearrange. Okay? So let's see what happens. E1 is an elimination reaction, okay? And we need to study these type of reactions. For now, let's just focus on the mechanism. Let's just focus on the reactions, okay? So if you protonate water, and there is a mistake in that diagram, in fact, that should be positive charge there. If you have to protonate water, this ends up being a very good leaving group. Now, OH minus, we've always told you, even at 11, it's not a good leaving group, but protonated, and it goes from being a very poor leaving group to a very strong leaving group, which means that now you end up with having a carbocation. Now, this carbocation can give 3 different products. Okay? This carbocation can give 1-butene, cis-butene, and trans-butene. The most stable of these 3 is the trans-butene. And therefore, that's going to be the one that is going to be created most. Okay? And therefore, it's going to be the one that is created most. Remember, it is not if at first you don't succeed, you're stuck with the isomer that you don't want. If at first you don't succeed, there are still protons, and they will still be able to then hydrogenate, okay, or add the proton and remove, add and remove until the equilibrium is reached. This on its own is a valid equilibrium. You don't need to start from the alcohol, okay? So even if you start with an alkene, you will always end up to the most unsaturated. And in fact, here we've seen that this was you had possibilities there and there for a positive charge. One was monosubstituted, and the other one was di. Whereas, let me make sure. For this one, this point was tri-substituted, okay, and this point was di. So it would be more stable. And in fact, terminal alkenes are always less stable than internal alkenes. So if you have to choose between a terminal alkene and a non-terminal alkene, always go for the non-terminal alkene. Okay? Always go for the non-terminal alkene. Okay? In fact, I do believe that that is wrong, because this should, in theory, if you have a positive charge there, it would have 3 alkyl groups attached to it. Okay? But it's about whether you're gonna be using that carbon or one of these. Apart from the fact that statistically speaking, you have 4 hydrogens versus 2, but that is going to be a story for another time. Halogenation, again, we're going to be having the same structure as before, okay, where you're going to create vicinal dihalides. Now, vicinal means on adjacent carbons, geminal means on the same carbon, okay? And the halogenation is the test for alkanes and alkenes, but to be honest, for this level, that is not that important. Maybe in the labs, but in reality, it's not something that I'm gonna be too fussed about. This is also gonna be anti-addition, okay? And this is predominantly anti-addition because the bromine is huge, okay? The bromine is huge, therefore it will always attack from the opposite side of where the previous atom has been. I do believe that for the other one, we said both of them could happen. Yes, this both can happen, okay? But the end product would be the same. Why? Because the single bond can rotate, okay? So whether it's anti or syn, the end product will still be a racemic mixture, okay? But bromine is huge. Therefore, the second bromine can only attack the structure from where the other bromine is not, from the anti position. Okay, so syn, same side, anti would be opposite side. Okay. Now, some reactions might then be slightly stereospecific. Okay, but this is only a kind of mistake, not because the reaction wants to be. So here we have two reactions, and we're gonna see that we're gonna get RR and SS. So this is a racemic mixture. Okay, but if we were to add the trans to butene, this will only happen, this will only form, okay, this will only form the RS or S star structures, and because it was symmetrical, it would be identical, okay, and that would be identical, okay. Now, I don't want to waste a lot of time on this because we will be speaking about this again later on. Okay, I would like to do the mechanisms in a little bit more detail, but let's start with the reactions first. Okay, but remember, you're gonna be adding these anti. Okay, so if I push these down, then the bromine will be from top, and it will be from the bottom here, and these will be up. Okay, but we'll be speaking about this later on itself. Today, let's just have a good idea. And the mechanism is here. Now, the mechanism, you will have a bridged, okay, brominium. So this is called the bridged brominium. But it's also possible to have the bromine attached to mostly one carbon. But anytime, the second bromine will always attack from the other side. Why? Because this is huge. Let's say, okay, that's the bromine, so the second bromine cannot attack. Okay? I normally like saying this. Let's say you're a guy and there's a girl at the club. There's a difference whether she's surrounded by big, bouncy friends or they're surrounded by midgets. If she's surrounded by big, fat people like me, you'd end up in a situation where, oh, we can't actually speak to her. It's fine. We have to try another way. And here they try the back door. Whereas if her friends are small, you can just push them aside. Okay? So this only allows for anti-attack. Now, apart from the anti-attack, if we were to look at the resonance forms, why the brominium bridge, so the brominium bridge is this one. That's a brominium bridge. is important, okay? It's because of the octet rules. Now, again, this is not always the case, and these reactions, you might have the sextet rather than the octet, but octets are normally favored. For example, with water, normally you end up with the oxygen might still be easily reactive, and they are very reactive because there would be some strain. So this angle here is 60 degrees, okay, which is definitely not the ideal angle for a reaction, okay, for a bond. Now, halonium ions can be intercepted selectively by other nucleophiles, for example, water. So once you prepare the bridge, you can add any nucleophile you want, especially if the bromine itself is in small amounts, if it is in small quantities. If you have water as a solvent, you will always end up with a mixture of the dibromo and the bromo alcohol, as you've seen in this reaction for last year. Why? Because the nucleophile can open up the bond, okay? Nucleophilic ring opening occurs at the more substituted carbon, Markovnikov-like, okay? In fact, this is because of Markovnikovs rule, okay? Even though we have the bridge, the charges might not be completely equal. So you'll always obey Markovnikovs rules in this reaction. But you know that the mechanism is slightly different. Instead of doing a full positive charge on the carbon, also the positive charge is going to be on the bromine. And here you can use this in synthesis, okay, to prepare either ethers. Now these type of ethers are going to be very important, okay? They are called epoxides, okay? Or you can use them in synthesis to introduce functionalities such as the alcohols, which you can then go on to produce ethers, to produce ketones, to produce aldehydes or ketones, okay? Carboxylic acids if they are at the end of the carbon. So there are a number of things you can do. And the bromine can be substituted to anything you want. Okay, so this is a good way how to introduce specific groups. And therefore, you can use halogens, okay, to prepare haloethers. If you were to attack, if you were to use an alcohol as your nucleophile. Now, remember here, look, remember here, realize this. He gave you the three components, but you need to know that first these two react, and then that comes to the picture. Okay, that is very, very, very important. Okay, and then you can introduce the halogen, an alcohol group. The alcohol group produces the ether, and that would give you an oxygen that is protected. Meaning, in your next reactions, probably it will be the chlorine that will react and not the alcohol. It will be the chlorine that will react and not the alcohol. Okay, so these are a few reactions that you might want to look at, and these reactions, okay, and these reactions you can see and you can analyze and you can understand in order to ensure that you know what the product would be. So here we're assuming that the blue one would be the electrophile, okay? And the pinkish will be the nucleophile, which is the most electronegative. I'm not going to tell you you'll be using these a lot in the lab, but these are very useful in organic synthesis, okay? So if anyone might be thinking about doing synthesis in the future, these reactions might give you a very good idea of what you want to do, okay? Now, any questions up to now? Okay.
For
Yes?
the alkenes, as in, what makes internal alkenes more stable?
It's the possible positions of the carbocations. that can be produced. Let's try and find it. Bestow. Yes. So it's the possible, let's say you have a hydrogen here. Okay? This carbocation is not going to be stable. Whereas if you have a hydrogen here, this carbocation would be. Okay? Apart from that, internal, you can normally shift the charge around a little bit more than external, but in this case, that's not going to happen. Okay? But it's where you're going to add the proton. Remember, this is an equilibrium, so the more equilibrium you're going to have, the better it will be. Apart from that, if you're going to add to the carbon that has most hydrogens, H and proton, and that would be H and proton there. And that would be pretty much the same structure. Now we're going to be analyzing this a little bit more when we do proper elimination reactions. So we're going to have, we're going to do 4 mechanisms for halogen alkanes. And these mechanisms will be SN1 and SN2 that you already know about. And the others would be E1 and D2. They are very similar to SN1 and SN2. But instead of substituting, okay, you will be extracting a proton and thus eliminating. So let's actually wait until we get to that position. Now, any other questions? Okay, I wait, we're going to stop the recording here.